Okay, so welcome, guys. Going to dive straight into what we are supposed to do today. Matrices and matrix operations. Believe we've all sort of come across it. I don't know. Can you guys unmute yourself? Say something. Yes, I know you're here. Darlene, Daniel. Hi, hi, hi.
Hello.
Yeah, hello.
Hi. Yeah. Hello, 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 hello. I think, Darlene, it's been long since you joined us. Are you on track? Are you up to speed?
Yeah, I've been what's it called? They've been sending recordings of the class. I don't join because at this hour my network is not really good most of the time. But then I join at the beginning and it falls off later.
Is that you saying you won't be with us at the end?
Oh no, I will. I'm at a good
Okay,
spot today.
okay. Thank God. And Daniel, hope you're also well. How was last week's session? Were you able to finish your assignment?
Yes, please. I was able to finish it. Um, and I went through the lab today as well.
Oh, okay, okay, great. Have I think I also shared a link to a couple of YouTube videos. It's a playlist actually
Yes,
of everything, so it will be very helpful. The videos are
yes, please.
short and
Yes, please.
yeah. So in your own free time, you could go into. It will be very helpful. Sometimes we are not able to explain it well. So yeah, darling, please go on.
Hello, sir. Please, I saw that they put a form in the group that we should fill for the project. And they are saying we can do it in twos and in threes. But then, okay, for me, I don't even know anyone in the class. So how do I decide who I want to do my project with? And then, what kind of like they said we should look for a problem now we think AI can solve and then build something. And like, I don't really understand the whole thing they are saying.
Great. Yeah. Well, first off with the groupings, I think you can do it alone. You can do it with a couple of people, or you can do it with someone else. I think one, two, or three. So if if you just apparently you could just reach out to anyone in the group, just see if they have a group member or they want to be in a group or something, and you guys can discuss a project idea. And that apparently you can just text anyone randomly and get someone to pair with, or you could get your members in your lab. So perhaps if Daniel doesn't have a teammate or if Daniel doesn't have a group or anything, you guys could hit it off and see if you come up with something, and that also works. So as for the groupings, it's at your own discretion. You could also come alone if you have something that you want to do alone. So you could also do that. The main confusion I think is with what you can do, what you can do, and all of that. Yeah, you can do anything you want, but then it should be in the scope of the course. That's why I would recommend, because what we are doing isn't machine learning its AI form. So you can't you technically it will be difficult to build an AI system like it. I'm just using AI because it's AI. But then it will be difficult to build something like complex or advanced. As you were saying, we haven't even done the calculus aspect. This is just the basic vectors and matrix and all. Matrix is also like vectors, multiple vectors, like low key. We'll get to that. So as for this, you just look for projects that you can apply some of the concepts that we did earlier. So for example, this is like just putting I'm just putting all my cards on the table. Like, for example, last week we did I think we did cosine
Well, you don't.
similarity.
Last thing, Kaba. Now I'm leaving. So last thing,
Yeah, Ryan, can you please mute yourself if you're if yeah. So I think last week we did cosine
Oh, I'm
similarity.
here, so
let me talk to you.
seriously.
Um,
No, like,
If yeah, so
when
kala
Hi
na,
you.
Ryan,
so kala na.
can you please mute yourself?
Stop.
I fell.
Hi
No phone,
Isaac,
no
Ryan.
phone.
I fell within the week. I think it was Wednesday.
You fell in the house or in the school?
Yes,
There's no
in the
way I
house.
can mute him too.
Maybe like comedy.
You cock back.
Maybe everybody never for my way. My dad, I can't remember. I'm not going to go because of a later family. They call me as a. Maybe I never seen how far. You the college telephone. The hell, my little telephone.
Hello,
My the father, woman. I
Isaac.
say, my
Can you
dear,
please mute
woman. Yeah,
yourself?
for me, kama jani the fumaguji. Makonya ba haji ko for
I'm
most of
coming.
you.
Hello, Isaac. Please mute yourself. Yeah, yeah. Thank you. Okay, so I was saying last week we did cosine similarity, where you could take a couple of vectors and just see how similar they are, right? And we've been learning that all these digital stuff are made up of vectors, and some of them are like vectors in vectors, which makes them matrix, right? So let's say if you on cargo here, there are a couple of data sets in CSV files, and trying to mimic something like the like 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 a movie recommendation system, right? So you could get a couple of movies, like let's say 5 movies or more. I'm just saying five so I can explain it easier. But then in data sets you have multiple movies. So like take these movies, compare them to each other, see how similar they are, and predict that if someone likes this movie, they're going to like this movie because they have a similar they are similar in terms of the cosine similarity, right? I don't know. Do you understand what I'm saying, darling? Do you understand what I'm saying?
We'll take it like that. It will get better soon.
No. Try, try to understand what I'm saying. So let me take it again, right? So soft like Spotify, right? Once you go on there and you start playing any random song. Most of the time, it doesn't end like when that song ends, it won't just end. Even if you are streaming an album and it ends, it's not going to end. It's going to play another song, right? It's going to automatically move to the next song and start playing for you. And it doesn't just pick the songs at random. It's using either songs you've liked or songs that are similar to what you were listening to. And they don't listen to all the songs and classify them, right? They don't do that. It's an algorithm that does the it's an algorithm that does the prediction or the suggestion, right? So what it does is in the most basic form, right? It's more advanced than this, but like what it does basically is that it's comparing. It's going to take all the music, all the audios are stored as numbers, right? They are stored on numbers, and at the most basic level, they are vectors. Okay, so these vectors you can just compare 2 or 3 or more vectors to see how similar they are to each other. So applying the concept of cosine similarity that we did, I think I think last week's lab also, you could find a similarity index between these two songs. And then the more closer they are to 100 or to 1, you can say that this and this are very similar. And so if you like this song, then you definitely like this song because they have they are very similar in terms of their structure at the vector level. I don't know, is this better? So So what I'm suggesting is building a music recommendation system. It could be any recommendation, like recommendation system in general that's going to use cosine similarity. You could use dependency of vectors to also think come up with something. But then this is just one idea that's going to be within in the scope of what we have done. Okay, that's one thing. That was what I was saying. Is this better? I mean,
Hello.
yeah. Hello,
Hello,
Hello.
Daniel.
yeah, I think it's better.
Yes, please.
I think Daniel, you
Can
also
I go on?
yeah. Please go on.
Okay. Please, for the cosine similarities, for example, the example that you made right now, you see, does it take the angle between the two pictures? I don't know how it works.
Do you
Does it
remember
take the angles and compare the angles? Yes.
so the cosine similarity formula? If you remember, it was the I think the dot product of two vectors all over the dot product of their magnitude. I think something like that. If you remember,
Yes.
yeah. So
Yes. The
uh,
magnitude of x and the magnitude of.
yeah, so that's all you sort of need. You have your vector A, vector B, and then you run it through the formula. I don't know if I don't know where the angles. I don't know if you get if you, I don't know where the angle part's coming or because the cosine this thing is measuring the angle between two vectors. Is that why you are hello?
Yes, please. I
Yeah.
think
So
it's because of I was thinking about this.
uh your line is breaking. Your line is breaking. Can kindly repeat yourself,
We'll
please.
get a hello.
Yeah, please
Hello.
repeat yourself. Yeah, repeat.
Okay. I'm saying that I was thinking of a radian result of the cosine calculation after they compute the cosine, and then they will compare the two vectors.
So from what I know about the cosine similarity, right? It's once even though you are trying to find the cosine of the angle between the two vectors, the answer that you get is going to be between -1 and 1. No matter what you do, it won't be more than -1. It will be less than -1, it will be more than 1. So the thing is that -1 is like direct opposite. One is identical and zero is perpendicular, or like they have no relationship or they're orthogonal. Okay. So that's the breakdown. So I think if it's one, if the answer you're getting is close to one, means the angle between them is zero. So yeah, I think you can also use the angle between them to sort of get a sort of insinuates in the output of it. So yeah, so let me track back, right? So once you are around the cosine similar, you're going to get either you're going to get the answer is going to be like in three folds. Either they are identical, they are not related at all. That's whether they are orthogonal or they are opposites. Like they are opposite. They are not. They are opposing each other, right? Different directions. And if they are in different directions, I mean the angle between them is 180 degrees, right? And if they are not, they have no relationship or they are perpendicular, it's going to be 90 degrees. And if they are very similar, identical, the angle is going to be 0 degrees, right? So the answer that you get is not going to be in degrees or radians. It's just going to be a number. It's going to be a number between -1 and 1. and the closer it is to one, you know that it's similar. The closer it is to -1, you know that it's not like it's direct opposite, and the closer it is to zero, you know that they have no relationship, or they are like, I don't know. Is this a better explanation? Like, do you get it from this, or I went off from your question? Hello.
Yes, yes, I can relate it now. Okay.
Okay, okay, okay. So yeah, the dialogue is even going online. It's even going offline. But I think you also having you're also not sure about the project thing. But I don't know if this example has clarified it a bit for you. You could think of something else, or you could use this. I don't know. Yeah. So let's go on with today's with the matrix and stuff. Okay. So something small about this. In ML, the data
Hello,
usually comes. Yeah. Hello.
hello.
Yeah. Yeah. Go on.
Please, I would like to ask if from today and tomorrow. Hello.
Yeah. Please go on.
Please, I'm saying that if I've not gotten I can change, or if you put a topic there, is it possible to change it later?
Yeah. I think it should be flexible in that regard. Yeah. But I think maybe after this session, if we go back and there's a chance to bring it up with Richard, you could bring it up, or tomorrow during tomorrow's class. But then I think it should be flexible for you to change if you want to. And I only got the ending part of the question, so I don't know if I missed something in the beginning. Your line was breaking.
Yes, it's yes. I get it now. I get it. Thank you.
Okay, okay, okay. That's fine. You're welcome. All right, so I'm going to go ahead and talk about today's one. We are going to learn about matrix and how to manipulate them in Python. Do the addition, multiplication, some scalar operations, and perhaps some vector operations as well. And talk about transposing matrices. I think we'll do that in the code, and also sort of visualize it to see what it actually means to transpose a matrix, right? Talk about symmetric matrices, and also some of the special matrices, the identity matrix, diagonals, and all of that. And as for the linear systems manual and computational tools, let's see, maybe we'll jump down and go to the image kernel rank and nullity of matrices. This is like very, very solid stuff in data science and even machine learning as well. And we could talk about how to verify your index of a matrix, how to index a matrix, and also verify the matrix indexes, and also some derivations. And uh, I'll try and I'll try as much as possible to make it make sense in machine learning space, right? So wish me luck. Yeah. Okay. So I think as for the theory and all of that, I mean, last week he said a lot about that. So just going to give something small from my side that will help me ease us into what we're going to do today, right? So usually in machine learning, whatever data it gets, it comes in multi-dimensional arrays, right? And matrices are usually best to handle some of these inputs. Most of the data sets you work with is it's not going to come in just one column. It's usually going to be multiple columns, multiple rows, and you need a certain structure to handle these things when you want to perform some arithmetics on them and all of that. You need it to be a certain structure, right? So when you say matrix, you're looking at any 2D array where the data is in the form of rows and columns. Okay, that's the only difference. That's the main difference, actually. Not the only, the main difference between vectors and matrices, right? As for vectors, it's either going to be in a row only, or it's going to be in a vector, or sorry, it's going to be in a column only. But for matrices, for matrices, it could be represented. It has to be, sorry, in the form of rows and columns, right? So in vectors, we're mostly working with I for I in range, right? We're working within one range, but for matrix, we're going to have I and J, because we have to consider the ranges of the column and the ranges of the row. So in whatever code, whatever you're going to do in the code, that will be one of the main differences that you're going to see. The introduction of um, a new variable, or I don't know if variable is the right word, but like going to see the introduction of J. So we have I, which represents the row, and J, which represents the column. And just to be clear, I think row is the the horizontal, right, and column is the vertical. Just to let me look it up and see. Yeah, so row is the horizontal from left to right, and column is the vertical from top to bottom. Right? Anyone want to say something? Okay. So yeah, so I represents the number of rows or the range of the rows. So I is rows and J is columns. Rows is horizontal, column is vertical. Right. So each matrix has an order that will represent the total number of rows and columns, and it's usually written as the rows times the column. Right. So the rows come first and the column comes second. So if we say a 3 by 2 matrix, it means the rows, we have 3 rows and we have 2 columns, right? Right. So that's that. And let's talk about how to define a matrix in. Let's talk about how to define a matrix in Python, right? So as you can see, matrix is a rectangular array of numbers. In machine learning, matrix commonly stores the data set representing rows and right. So m by n, rows by column. Rows comes first, column comes second. All right. So this is a matrix, a 3 by 2 matrix, where we are trying to mimic a small data set. We have 3 observations and 2 features. Features also means columns, right? So 2 columns and 3 rows. As a Python list of lists and as a NumPy array. So that's the difference. That's also like one of the different. In the vectors, anytime you want to represent vectors with pure Python, represent it as a list. But if you want to do it with NumPy, it becomes an array, right? And same for matrix as well. Just that, as I was saying, matrix is multiple vectors. So in Python, we create something called a nested list, right? So let me just use what we have here. I need to type. Right. So for houses over here, as you can see, we have our first row, which is 1500 by 3. Second row, this is our second row, and this is our third row, right? And this is a 3 by 2, right? A 3 by 2 matrix. So check it out. Once you print this, see how we had to call it with pure Python. We have to write it in the form of a nested list. So this is a list. This is also a list. This is also a list. And we had to write them in multiples with commas as the separating values. And then it becomes a nested list or a list of lists, right? And that's how we can call it in, well, that's how we can represent it in pure Python code, right? So for our in-house is print R, and then that's what we have over here, right? So now look at it in NumPy. This is our data sets. We didn't have to specify the range for it to print everything for us. All we had to do was to tell NumPy that this is an array, so print it out for me, and then voila, that's what it does. Right. So you can check the shape of the vector, or sorry, the shape of the matrix, and you can see say it's 3 2. So the rows are 3 and the columns are 2. It's a 3 by 2 matrix. Okay. All right. So let's go on to talk about the matrix addition. You can only do this when the two matrices have the same order. Okay. If they are not same, if the order is not the same, like if they are not the same in terms of the shape, you will not be able to do an addition. And this is like something. This is like very important when it comes to convolutions in deep learning. You know, images are just matrix like this, and sometimes should I I'll say this at the end. Okay, remind me. This will be the link thing, so I'll come to that at the end. Right. So you can only do the addition when two matrices have the same order, and it is done using the addition sign, the plus. Okay. So it's just going to add corresponding elements of the matrix. So if you have two matrices A and B, it's going to add where I. So, how do I? Let me just demonstrate it with this. Right, it adds it like element wise. So if you want to add a matrix, it's going to be 1 plus 5. So this plus this, so 1 plus 5, that will be our first okay, take a look at the output over here, right? This is our first matrix A, which is 1 2 3 4, and our second matrix B, which is also 5 6 7 8, right? So A plus B is essentially this first element in A plus the first element in B. So 1 plus 5 6, and the second element in A plus second element in B, 2 plus 6 8. Same for the third, 3 plus 7 10, and then 4 plus 8 12. So it's adds it's like element wise. Um, that's why it has to be of the same order. If it's not, if they are not equal, you won't be able to perform the matrix addition on them, right? So it has to be of the same order. So addition and subtraction are like it has to be of the same order. So it's pretty simple with in Python, not as complex as the other one, because all you have to do is to introduce your plus sign, right? As I was saying, we have to specify the rows and columns. Okay, you have to specify the rows and columns, because in with lists, if you don't specify, it's just going to take only the first one, leave the rest. So you have to make sure that it loops through everything we have. And as I was saying earlier, in the vectors, it's just going to be you. It's just going to be with I. But now here we have J, which is the columns. So for J in range of the length of our first matrix here, right, and for I also in the range of the length. So we specify where we want you to loop this. We want to loop everything in. Okay. So that's the main dynamic. Anytime you are doing any matrix looping, or if you are doing the code with pure Python implementation, you have to specify the I and J ranges. And once you do that, it's going to do the addition for you. Okay. But with NumPy, you don't have to stress on all of that. Yeah, Daniel, please go on.
Please, hello.
Yeah, please go on.
Please, for the I, you didn't put any index on it. The A pi, you put A pi 0. And then the second one, you didn't put the A pi, any
Yeah,
index
yeah.
on it.
So
I don't know why. I actually do not understand it.
okay. So J is the column, sorry, and I is the row. Okay. So zero is essentially the first value in Python, in coding and in Python, or let me just take in Python, right? So what we are trying to say is that for the length of our first vector, it should start from the first column. Okay. And once we already specify for that, we don't need to do it for this one too. It's automatically for the I in range, it's automatically going to start from the first one. But because of the columns, we have to indicate that let's take it out and see what happens. And then let's take it out and see what happens. The code. So let me run this. And yeah, so it didn't even it didn't change anything. So perhaps we don't even need it. But then it's just sort of specifying that it should start from the first column and not from the second column because of the way it's arranged over here. Once you don't specify, it might probably going to add it separately with the pure Python, because it's just lists. You have to be specific about how you want it to work. So in case we don't have this looping function over here, even it's going to do something differently for us. Okay, so with a pure Python, most of the things you have to be specific about it, but then you can also experiment with it, do something the other way around, and see what happens. I'm trying to see what happens if we don't have, right. So you see, it's saying that it's out of range because we didn't specify the range that we wanted to work with, right? So just to avoid some of these errors, most of the time you just include it just in case. But then you see, we didn't really get any error when we're trying to do it. But then if there was to be an error, the first thing to do is to specify where you want to start from, which is what we had in the brackets over here. Okay. All of this is cut off if you use the NumPy approach, which just treats it as an array. So the arrangement that you have it is going to move in that order. And all you have to do is just to tell it what you want to do, whether I want it to add or subtract. You just have to indicate with the operator over here, and it's going to do the calculation for you. Okay, so that's what we have over here, and you can compare the results of both of them. We see that it's the same thing, right? 6, 8, 10, 12, and same for the NumPy approach, 6, 8, 10, 12. Okay, and please, if you want to jump into something, just unmute yourself and talk, because once you raise your hand or something, I won't be able to see it till I come into the interface that we are in, right? And because I'm in cargo, I don't see what's going on over here. So just unmute yourself and cut me. Okay. All right. So let's talk about the. So this is it's still the same for subtraction. All you have to do is just to change the operator, bring the subtraction, and then it works for you. Okay. So the next thing is the scalar. multiplication, which is also just I don't know if I think I didn't join last week's session, so I don't know how he explained the multiplication for you. But then it takes two parameters for since you want to multiply maybe x and y, you have to take like guess x and y values, and then each of this is going to be expected to be a list of lists, right? And we do the computing. So let's check the real Python. Right. So what I was talking about was this matrix. I'll come out to the scalar multiplication. So let's look at this multiplication first. All right. So we have 2 by 3 and 3 by 2 matrix, and we want to multiply them, right? As for the the multiplication, it doesn't matter. They don't necessarily have to be of the same order, because it multiplies like, how do I even explain it? Each of the elements multiplies themselves like one by one, all through. So it doesn't necessarily have to be of the same order. It can still do the multiplication. So let's look at the function we have here for the Python one. The first line, the def matrix underscore multiply into bracket x and y. It's just taking the parameters that we use, the two matrices that I want to multiply. If you have three matrices that I want to multiply, all you have to do is to make room for that. So you add it to x, y, z, or whatever you want to use. And it has to be a matrix, right? A list of lists or whatever. And then the next line, which is the result equals our square bracket 0 for underscore in range, right? 0 for underscore in range of the length of y, also specifying where we want to start from for underscore in range length of x, right? So this line is just creating an empty results matrix, which is in the beginning is going to be filled with zeros, right? So length of x is the number of rows in x, and length of y is also the number of columns in y. Okay, so the resulting matrix will have the number of rows, which is the same as x, and the number of columns, which is the same as y. And the inner parts just create one rows of zeros for as many zeros as they are in the columns of y. Okay, so the next line, what do we have? The for I in range length of x. That's right. So for I in range length of x is just going to repeat that process once for each row of x. Okay, so just like looping, as we said, looping through each row. And for example, right, if x is say a 2 by 3 and y is a 3 by 2, then our results become a 2 by 2 matrix, based because of how the matrix calculation is done. And you can, I mean, if you take your time and go through how the calculation is done, I don't know if he explained this multiplication, because I'm finding it difficult to explain how it's done, like with just the code. I feel like I have to write it, but I'm not sure how to do the writing. Yeah, so if you remember how he explained it, I mean that's what I'm trying to replicate in the code. Yeah, so that's exactly what we are doing over here. So the loop will go through row by row for matrix x, and I is going to be the current row indexing x, right? That's for the I in range leg. So we're going to wherever we are starting from, that will be our starting point, and it's going to loop row by row for that length of the matrix. And then we go on to do same for the column. That's for j in range of the length of y. So the rows of the x matrix multiplies the column of the y matrix. That's the best way to explain it, right? Okay. And then we initialize a temporary variable which is s. This is the s is equal to 0 for sum to accumulate the values of this. So as it's multiplying, it's going to sum it up. Okay, if you remember the formula, it's the summation of the multiplication of x and y. So the multiplication is the rows times the column. I mean, this is that's like normal mathematics matrix. How did they calculate the multiplication? Rows times column, row times column, row times column. Then you sum it and get the first value. Do the same and sum it and get the second value. So in the end, you realize that your output matrix will shrink. Yeah, so it will shrink. Yeah, it usually shrinks. So that's the concept of doing convolutions as well. And then the loop will also run through each element in the row of x and the corresponding elements in the column of y. And k will just represent the shared dimension index between the two matrices. So for valid matrix multiplication, the number of columns in x must equal the number of columns in y, but then it doesn't really yeah, it doesn't really. I mean, it can still multiply either way. There's the output will reduce or increase depending on how the multiplication is done. Okay, so that's what we are. That's what's going on in the normal in the pure Python code. And the last but one line is the results. This one results ij equals x. So once the innermost loop of the pure Python code finishes, that's where all the summing and the products and everything is done. We're going to store the computed value, which was s, that we had, into the correct spots. That's the results matrix, right? And then we return the results. Okay. So this s, we're going to store this calculation, this final thing that is done here in the results where we have our row and column, and then we return the results. Right. So the parameter the variables that I'm using for the pure Python, you can see them a underscore pi2, a underscore pi2. So we pass in our matrix as nested lists, and then we just call the arguments. We call our function, which is the matrix multiply over here, pass in our x and y. X is a, y is b, and then it does the calculation for us. Just loops through the function. As once again over here, it's easy, right? It's called dots multiplication or dots products. Multiplication in matrix, multiplying two matrix is just literally dots products of them, right? It's not like the normal multiplication, like scalar multiplication. It's just dots products of them. So all you have to do is to say just call the dot function of NumPy to do that for you. I think Richard wants us to even switch to only NumPy because the pure Python is usually complicated. That's why we have the libraries there to help us. So me, the assignments I'm giving you, you'll be using NumPy a lot. Just trying to just understand what's happening in the cell, or what's happening in the calculation, what calculation you are doing, and then know what function to use. Right. So we have our first array. These are data sets, which is just a list. We convert it to an array for NumPy to be able to do the computation, and then do the same for the second one. And then all you have to do is say a dot b, and then that's it. It understands that you want to do the matrix multiplication, and then you get your output. So you still see we have the same outputs, but then this is a bit more complicated because we are doing like that's matrix multiplication. That whole matrix multiplication thing is like it's a lot of processes. So the loops you need to implement that is a lot, right? But with NumPy, just one function, dots, and then you're good to go. Okay, so let's talk about the scalar multiplication. It's just like the vector scalar vector multiplication. It's just increasing your matrix, right? What's matrix? So we use a underscore pi. A underscore pi is 1, 2. Let me bring it here so we can see it's over here, right? So a is 1, 2, 3, 4, and then you multiply by 3. So because the scalar multiplication, you're going to multiply each of them. Like that scalar values is going to multiply each of the values in the matrix. So 3 times 1, then we get our first value 3. 3 times 2, 6. 3 times 3, 9. 3 times 4, 12. And that's what we are doing over here. So this is our scalar value. We say this value should multiply our matrix for the range of the range of the length of the column and the range of the length of the row, and then get the outputs. I think this could go, and we should still get the we should still get our output, right? Apparently, right? I think someone took the presenter role, so taking it back, and I'm going to share my screen once more. Okay, so the scalar one is pretty simple. So it's almost like the addition. Just have your scalar value and do the multiplication. So with this multiplication sign, it's going to do the scalar multiplication, but then it's not the same as the actual matrix multiplication, right? So take note of that. So let's talk about the special matrices. So special matrices have structure that makes them easy to reason about. We have the identity matrix, the zero matrix, the diagonal matrix, and the triangular matrix. And I think the first one we're going to do is the identity matrix. Okay, so we have zero matrix, identity matrix, and the pure matrix, so the diagonal matrix. So all of three are going to try to interpret it. So let's see what they look like. So this is a zero matrix. Everything is zero, right? All your it's just zeros, and this is also like very important in ML. I'll try and if there's time, I'll try and explain that too. And then identity matrix, you have um how what's the best way to even explain. So with the identity matrix, it's usually a square matrix with ones, that's like ones on the main diagonals, and zero will be everywhere. So the diagonals is going to be filled with ones, and then you have zero everywhere. And with the diagonal matrix, or the exterior, right? It's also a square matrix, like just like that, where all the elements outside the main diagonal is zero. As for this one, the diagonal doesn't have to be one like the identity matrix, right? Identity matrix, the diagonal has to be one, but for the diagonal matrix, it could be any value, but then it has to be on the diagonal, right? It has to be in the main diagonal. Okay, it could be any number, including zero, even, but then that diagonal part is full. So 1 0 3. It's a diagonal matrix. It could be 1 2 3 over here. It could be, but once it's all ones, it's identity, and once it's zero, it's a zero matrix, right? So that's what we are trying to replicate over here. Once again, with the NumPy, all you have to do is to call the functions. They already have inbuilt functions that you have to specify the size of your matrix you want to do, right? So this one, say we want to create a 3 by 3 matrix, a 3 by 3 matrix, but like it should be zeros, and then it does it for you. Once you say np.zeros 3 by 3, specify the kind of matrix, you get zeros. It also works for vectors. Once you specify the length of the vector, the length of the vector, you also can be kind of, so you can also get a zero vector, right? And identity matrix as well, specify the size, 3 by 3 matrix, and then is this dot I function. That's the identity matrix for you. Same for the diagonal. You have to specify the values you want to fill the diagonal with. So over here, we specify that our diagonal value should be 1 0 and 3. It could be 1 2 and 3, and then you see that it will change in the code over here. So 1 2 and 3 is now a diagonal matrix. And once you just specify this dot diag, np dot diag, you're able to change the matrix to be a diagonal matrix. But with the pure Python, you have to specify the ranges as usual, right? And I mean the outer list, which is the for underscore, the outer loop, the for underscore in range 3, just saying that run 3 times for each row of the matrix. Same for the inner list, saying create a list of 3 zeros representing one row, right? That's the 0 for underscore I in, for underscore in range. Okay. And so together, we are just creating a 3 by 3 matrix, 3 rows, 3 columns, where every entry is zero, right? And that's for the zero matrix. And then you get every element to be zero. For the identity one, let me see. For identity one, right? Our outer loop, that's for I in range of 3. It just iterating over the rows. J in range of 3 is iterating over the columns. And the inner one saying 1 if I is equal to j, put 1, otherwise put 0. So if the row index I equals to the column index j, put 1. So if we are at row 1 and column 1, put 1. If you are at row 1 and column 2, put 0. Row 1 and column 3, put 0. If you are at row 2 and column 2, put 1. If you are in row 3 and column 3, put 1. Right? That's what we are doing. Anything else should be 0. Okay, so identity matrix, the diagonals are actually where the row and the column like is the same value, and if it's like the index are the same, that place should be filled with 1, and that's what we're doing in the identity matrix, right? And let's talk about diagonal. It's almost like similar to the identity matrix, but we have already defined the values that we want to appear on the diagonal matrix. So say the first one should be 1, second one should be 2, third one should be 3, right? So we specify using the same row column looping idea. You say for each I row and for each j column, if I equals to j, place the corresponding diagonal value, right? Anything else, 0. Okay, so this also, you have to the depending on your size of matrix. If this was a 4 by 4 matrix, we need 4 diagonal value files, right? The diagonal value, what was the word? Values, right? So let's play with that and see. It's okay. So I mean, what depends on what we have over here. If this was going to be 4, let's say let's say I'm not going to touch the range values over here. See what happens over here, right? It's automatically going to do another value for us and fill everywhere else with zero. So your diagonal will specify the size of the what's it called? The size of the matrix, right? So depending on the number of values over here, your matrix keep increasing. You don't have to specify whether it should be 3 by 3 or 4 by 4 and all of that. Okay. Okay, so I'm going to pause, stop my recording and do it again because I have just 1 hour. Okay. So the next one is transposing and also saying symmetric matrix, right? So, oh, this thing is not recording. Okay. I don't know if I think I'm not going to talk too much about the what do I say the math, the theory of transposition and how transposing works, but it's just changing the shape of the matrix. So if you have a 3 by 2 matrix and you transpose it, it becomes a 2 by 3 matrix and all of that. And this is what it's going to look like. So it is a matrix. This is a 3 by 2 matrix. 1, 2, 3, 4, 5, 6. Right. Once you transpose it, it becomes a 2 by 3 matrix, which with the values that's of flipped. So 1, 4, 2, 5, 3, 6, which also still reads 1, 2, 3, 4, 5, 6. If you like look at it, if you transpose it back, right? So transposing it just literally mean just it's just me it just means flipping your matrix, right? And again, with NumPy, it's simple. Once you've specified that your list or your matrix is an array over here, that's the first thing to do. Make sure to convert it to an array, and then you want to do the transposing. All you have to do is say np, just call this t capital T value, and that's the transpose function in NumPy. So I want to transpose this matrix, and then it flips it for you. So as for NumPy, there's not much to say about it. Easy. And same with the Python. Almost the same, almost very similar to our row column looping, which we've done lots of times, right? It's just going to loop the same 3 times for each column in A. Loop an I variable. The variable I will become our new row index in the new transpose matrix, and then for each column I, we're going to collect the elements from each row J, and then we'll fill it in, right? So yeah, so it's basically what we've been talking about, right? So we see this flipping over here. A now J is first and I is second. J is our columns and I is our rows. So that's where the flipping is done, right? Once you switch it over there, it switches. Let's see what happens if it's I first and J second, and run out of range. So this okay. Right. So I think there's a visual demonstration of what it looks like to do the transposing. Right. This is our original matrix 1, 2, 3, 4, 5, 6, and transposing it. This is what it looks like 1, 2, 3, 4, 5, 6. Right. Flipping the matrix. Right. And as you can see, the shape will change. Initially, it was a 3 by 2 matrix, but once you transpose it, it becomes a 2 by 3 matrix, and it's just turning it clockwise by 1, and then flipping it horizontally. So the 1, 2, 3 will come to the left side, and the 4, 5, 6 comes to the right side. Yeah, that's what's done over here. The next thing is the symmetry. Symmetry. And how best to explain the concepts of symmetry. A symmetric matrix looks the same when it's flipped along its main diagonal. So the way to check for the symmetric property of the matrix is just to, so we have two ways, right? As usual, the NumPy and the and the pure Python, right? With the NumPy, it's this function that we used to do check check if the matrix is symmetric. So this is our S. This is the matrix we are going to check for this for the symmetricality of the matrix. 1, 2, 3, 2, 5, 6, 3, 6, 9. So np dot all close call matrix that we want to do, and also transpose it, and then we check the symmetric. So it's being symmetric is just comparing it to its transpose form to see if they are symmetric. And that's what we're trying to do over here too in the pure Python code. We This is our original I and J, and this is our transpose, which is JI. So J comes first and I comes second in the transpose one. And then checking, so this is just to check if this is in the range, if these values of S is in the range of these values of S. So just comparing that in there are different forms, are they symmetrical, and then we get a boolean output for that. Does anyone want to say something? I think someone's mic is on. Okay. Yeah, so let me just take it over again. So the length of S is the number of rows and columns, since S is a 3 by 3. And then the nested generator expression over here too just goes through every possible pair of I and J in the matrix. Alright, so for each pair, it's going to check whether the element at position IJ is equal to the one at position JI. And then that's what a symmetric matrix means. That's whatever value we have at position IJ is equal to whatever value we have at position JI. And then confirm that whether it's, and the output here is going to tell us whether it's true or false. So this is a boolean output, right? So true or false, and then as you can see, it says it's symmetrical. So yeah, and then the visualization over here, right? So I think I mentioned we can still do this over here. So solving AX equals B is central in ML for a 2 by 2 system, right? So this is our A, which is a matrix. X is a vector and B is also a vector, right? So we're saying A times X equals to B using Cramer's rule or inverse when invertible. So taking the inverse of a matrix, this is the formula for that. 1 over the determinant of the matrix times the inverse times, this is the what's the word? Discriminant.
Cofactor.
Sorry,
Co- Cofactor.
the cofactor, right? That's the okay. I think is the determinant or okay. I don't remember. I think cofactor. Yeah, cofactor. Yeah. So yeah, so it's just the one over the determinant of A times the cofactor of the matrix, and then the determinant is what we have over here, which is AD minus BC. Okay, so I'm going to use the NumPy approach to explain it, right? So this is our A and B. A is 2, 1, and 1 3, right? Which is a 2 by 2 matrix. And B is 8 and 13, our vector. Okay. So with our NumPy, that's why it's called the linear systems and solving, because that's what the function is called, linear algebra dot solve. Once you call this function, pass in your A, which is your matrix, and B to be the vector, it does the computing for you, right? And that's basically it's with the NumPy approach. And you can also verify that this is the inverse is actually right by using by multiplying the inverse of the matrix by the vector is b and p, and you're able to verify, right, if they are actually able to verify. Yeah. So then you're able to verify if the this is actually right. It's actually the right thing that was done, right? So with the pure Python over here, have same, yeah. So this is the same the same vectors that we were using, and using pure Python to solve via the closed form. Okay. So define matrix A, and then vector B, and then go on to we have four entries, right? We have A, B, C, and D, and see how we named our variable b underscore, just so it doesn't clash with the vector b, because we already have a vector at the right hand side, which is b, right? So just to avoid the clash, we right. So this whole thing is just to find x, right? Just to find x, and you can find it with yeah. So you can use so that's what we have over here, right? Use the inverse or the matrix to find x, because ax equals to b, x is equal to the inverse of a times vector b, and this is how to find the inverse of a using the determinant and the cofactor. and then determinant is AD minus BC. Count, count. And that's what we're trying to do, right? So with the NumPy, as I said, you can use this linear algebra.solve to do that to do that calculation, or you could use the inverse approach as well. With the linear algebra.solve, all you have to pass is your a and b, and then you can do that. With the inverse approach, you have you when you call you find the inverse of this times the vector over here, which is like this formula over here. So the inverse of a times the vector of b. So with the pure Python approach, you could take either of them, right? We could do it this way to get our x, or I mean, yeah, I think that's the way. So, or we could use the determinant approach as well. So yeah, so I think which of them are we using over here? I think we're using we found the inverse using the determinant, and then we multiply it, so using this value to find x, this approach to find x, and that's what we are doing in the code, right? So compute the determinant of a, which is the debts. Yeah, want to say something? Which is the debts into bracket a, and that is essentially a times d minus minus b factorial times c. That's the right minus b times c, which is 2 times 3 minus 1 times 1, right? 6 minus 1, 5. That's like calculating the determinants, right? With the formula. Okay. So that's what we were computing over here, where we have a d minus b times c in the with this determinant over here, right? And then the next one is to find the inverse. Okay, so inverse is 1 over the determinant of a times the cofactor, right? And is the this is almost like it's just like scalar multiplication. Okay, so that's how I did it over here in this code. Take the 1 minus that a and multiply it through all. Okay, so this times d, and this times minus b, this time minus c, this times a, and like that's what we are seeing in the code over here. So 1 over that a times b times d is just d over that a, and all of that, and so on and so on. So it's just like scalar multiplication, and that's what's going on over here. And then we did the multiplication of the inverse times the vector to get the solution to x. And so I mean that's that's what that, so like finding x, that's what we did over here to find x. And I think I don't know if this explanation is better, but then I feel with the videos I sent and all of, if you go back, you'll be able to make sense out of it. But then that's the breakdown of it and how we got it, right? So we have 2.1 and which is just 2.2 and 3.6, and same thing with the NumPy approach as well. Okay, how long do we have? 10 minutes ish. Okay, so the next, I think the last thing is the image kernel rant and nullity, and this is also a bit complicated and complex. So let's try and follow as much as you can, please. Right. So a rank is the number of independent columns, something the dimension of an image, right? And the nullity is the number of independent vectors in a null space, right? And an image or a column space, it can also be called a column space, is all possible outputs of A of X, and the kernel, which is also the null space, is all possible outputs of the kernel, right? And how I'm trying. Let me do step by step, right? Let's start with the image, right? Think of an image as all possible outputs of the matrix when you multiply it by any vector x, right? So you have your image, which is matrix A, and you have a vector x. Let's think of the image as the range of all the possible values or possible outputs of the matrix when you do that multiplication. So like A is let's say a machine that takes a vector in and spits another vector out. So the image is the set of all the vectors that the machine can possibly bring out, right? And it all depends on the vector that comes in. So if the machine only produces outputs that's along a flat plane, then then its image is in that plane. Okay, so that's like let's explain the image in that sense, right? And the kernel is also the set of vectors that the matrix can send to zero. So you like your matrix machine is spitting outputs out, right? But then there's a particular kind of vectors or inputs that when you feed your machine in, you get zero. Like the outputs, there's no outputs, right? Your machine is not able to churn out any outputs, or your machine just doesn't get nothing comes out. So that inputs is the kernel. Okay, so the image is all the possible outputs that the matrix can bring out, and then the kernel is the vectors that the machine takes in that makes the output become zero. God, this is I don't know if I'm explaining it right, but like that's breaking it down to like the layman terms for us to just understand what we're trying to do in the code. And the rank is the number of independent columns or rows. That's the dimension of the image, right? So it tells you how many independent directions the matrix possesses. So if the rank is 3, it means it fills a 3D space. If the rank is 2, it means it only spans a 2D plane, right? So in what examples we are doing so far, the rank is 2, which means that all the outputs is in the 2D space, right? And talking about the nullity, it's also the dimension of the kernel. The kernel, as I said, is the vector that's going to make your machine bring an output of zero, right? So the number of invisible or the number of outputs direction of input direction that's gets squashed to zero. So in how many ways can you move in the input space without changing the outputs since you still end up with zero? So that the whole theorem about the rank and nullity is that your rank of your matrix plus the nullity of a matrix is equal to the number of columns of the matrix. So if our rank is 2 and nullity is 1, then the number of columns will be 3. And like that's how we're able to prove some of how that's like the idea behind whatever we'll be doing in the this whole image ranking and nullity and all of that. So let me see if there is a Python part of the a NumPy part. So we start with the NumPy. So we have our matrix A underscore NP, which so A underscore NP is an array of this matrix, which is A underscore sample. So this is our matrix, right? And then we converted it to an array, specify the data type should be a float, so that we can get decimal values and all of that. Okay. So how do we find the rank with NumPy? just call the function matrix underscore rank in the linear algebra library. So we say np dot linear algebra dot matrix underscore rank. We pass in our matrix or our array, and then we get our rank. So it says our rank here is 2. That's with the NumPy one, right? And then this is doing the null space. Give me a second. All right. So I was saying with this one, you get so as for the rank, normal, you get your rank value, and the USVT is singular value decomposition. Can I look this up? Singular value decomposition. Let me type it over here. Singular value decomposition. SVD. So later when you're going through the code, you see it so that you can just check it out and see what it means, right? So with a singular value decomposition, U is the left singular vectors, which is related to the column space. S is the singular values, which tells us how many independent directions exist, and the VT is the right singular vectors related to the rules, right? The rule space or the null space, and that's maybe just of how to explain it. But like we are looking at the singular values, any that are effectively zero and corresponds to the directions with no information, which is the null space, and we extract these corresponding values from BT dots the transpose of BT. So the null space will contain the basis vectors for the kernel of the matrix. Yeah, I don't think this will work. It looks like the explanation is not making sense, and totally understand if you don't understand too. And then I think once you go through on your own, you'll be able to get it. Just but then yeah. So those are the values that we use to do the calculation for the nullity, right? Because we need to get the values of the null space, and then those are that's what we need to do that calculation, and it makes this over here very complicated because it's a lot of things we're trying to do over here. So I'm not even going to talk about this part, but then I think if you get a theory of the nullity, you appreciate what's going on in the code. You understand what's going on in the code, and we have 2 minutes left. I want to use it to just talk about the machine learning or the practical aspects of this. So this is inverse. As for inverse, I think we met it earlier. Even it's just 1 over the determinant times the cofactor. So just once you go through over the code, we did it earlier. So no stress about that. As for the rank and the nullity, I feel like you have to read this yourself and get the theory well, and then the code will make sense to you. Okay, so just trying to talk about the connection over here for stuff like image processing, especially, right? All images are tensors, right? Images are tensors, which is almost like matrix, right? It's just like but by a multi-dimensional array. It could be 3D, right? It doesn't necessarily have to be 2D. Just like matrix, right? Tensors can have any number of dimension. So that's how images are in like in digital form. They're just matrices. Let me see if I can pull something up. Images. And so that's how the when someone say pixels and all of that, pixels and voxels and stuff like that. How do I pull this up? Okay, I don't know if you can see this. Yes. So see the image is on the left side, and the matrix form the image on the right side. So this is like a very basic form of image, but then the image values they range from